Time to do worksheet 5. If you have not tried this already yourself, please go ahead and do that. And pause this video. If you have done it yourself, then you can watch here and see if we have pretty much the same answers. So here I've got a motion map. Something here, it's starting here. This would be at time 0 and then time 1, 2, 3. And I want to describe the motion of the object. So I think that there's 3 things to say. Where does it start? How fast is it going? And in what direction? So I'm going to say the object starts at position 2 meters and moves forward, or you could say the positive direction at, let's see, how fast is it going? It's going 2 meters, and they say the dot is, each dot is 1 second, so 2 meters from here to here in 1 second. And that's all there is to say. It starts at 2, and it's going 2 meters per second in the positive direction. Represent the motion with a quantitative x versus t. If you realize that this is the intercept and this is the slope, then, I mean, boom, you can just do that. That's easy. If you want to just transfer this information, 1, 2, 3, like one point at a time. I'm going from 2 to 8 here, so maybe I should scale this by 2s. 2, 4, 6, 8. So at time 0, I'm at 2. There's my intercept. And then at time 1, I'm at 4, at time 2, and so on. And there's my slope of 2. If you're looking at this saying, wait, that looks like a slope of 1, we scaled this by 2s. So that's a rise of 2 over a run of 1. All right. What does the velocity versus time? Well, this has a constant velocity, and the velocity is just the slope. So it's just constant. That's the velocity. It's 2 all the time. Write a mathematical expression that represents the relationship between position and time. That's just asking you to write the equation for this line. If you're just realizing that now, pause the video. Got to make this video watching interactive. So position, I'm thinking y equals mx plus b. I'm not going to use those letters, except there's an x there, but not going in the same place, right? Position, x, is equal to the velocity, which is that, times time, plus the starting position. You must have these units in that. All right, from the position time graph, find the displacement from time 1 to time 3. Well, at time 1, it's at 4, and time 3, it's at 8. So final minus initial, that'd be 8 minus 4 would be 4 meters. That's how you find displacement, right? That's the position at 3 minus the position at 1. Final minus initial. Find the area under the velocity time graph from time 1 to time 3. Well, here's 1 and here's 3. So that area under just means the area between your velocity graph and the axis. So that would be this. Now, just have to be careful about the scaling. This is like some kind of rectangular shape, so I need the height of it and the width of it. So remember that height is not a word. Height, with a hard T on the end, is a word. Height is not a word. So that's too high and too wide. Just have to, if you're looking at it going, yeah, obviously McGrath, but you just have to be careful and remember how you scaled things, right? It's possible that it could be scaled by something different than 1s. So 2 by 2, that's that area is 2 meters per second high times 2 seconds. That's the units here. Alright, so 2 meters per second times 2 seconds. Seconds cancel and I get 4 meters. Hey, how about that? So what does this area represent? Sorry, I didn't mean to cross that out. I was trying to underline it. What does this area represent? This is the displacement. It's another way of finding displacement. The area under that. Cool. All right. From the position versus time data below, right here, answer the following questions. This isn't a question. Who wrote this thing? Construct a graph of position versus time. Okay, can do. So 0, 0, 1, 2, 2, 4, 3, 4, 4, 7, 5, 10, 6, 10, 7, 10, 8, 5, and 9, 0. All right. Reach into this drawer and get a little straight edge here so I can make this graph nice and pretty-like for you. Oops, I messed that up, didn't I? So those are supposed to be at 10, and I made them go to 11. This one goes up to 11. That's a reference to the movie Spinal Tap. This is Spinal Tap. It's a satire of a rockumentary from a long time ago. It's very funny. Highly recommended. It's probably not school appropriate, but I don't know. I feel like you're old enough for that sort of thing. It's real, like, culturally important stuff. It's early on, if you know those other like spoof documentary things like the Best in Show and Mighty Wind that those people made. It's some of those people. If that all means nothing to you, then, well, just thought I'd talk for a minute while I was making my nice graph. Ooh, look at how pretty it came out. Construct a velocity time graph. Now, look at, that's the axis there. So I can have negative stuff. Okay, so from time 0 to 2, remember the velocity is the slope of this, but that's changing. So I'm going to have like a piecewise thing here. 0 to 2, looks like the slope of this, which is just scaled by ones, is 2, right? It's going up 2 every time it ticks over 1, the time column. So it's 2 for the first 2 seconds. And then it looks like it's 0, not going anywhere for a second. And then here, looks like it's 3 for 2 seconds. And then 0. And then it looks like it's -5. 1, 2, 3, 4, 5. For 2 seconds. So that's what these graphs are going to look like. These velocity time graphs, when we have constant velocity, are either just going to be constant one horizontal line, or if it's like switching between different constant velocities, then we're going to be switching between different pieces of horizontal lines. Motion map. Okay, so let's see. If this is 0 meters, then 2, 4, 6, 8, 10 meters. I'll go by 2s. I start at 0, and at my first tick I'm at 2. It's at time 1, and then at time 2 I'm at 4, and then I'm at 4 again. I'm going to drop down for that to show that it's at the same place, and that time ticked by, and then up 3. And then up 3 more, and then 2 ticks, 2 more ticks at the same spot there, and then back to 5. So I'm trying to line these up. All right, so that's the dots of my motion map, and then draw arrows that go halfway to the next place. Of course, if you're standing still there, then there's no arrow. The arrows indicate some velocity. And if you make it nice and carefully and really go halfway, the fact that this arrow is a little bigger than this one, since I went halfway to something that's further apart, it gives me, helps me see that it's going faster here than here. And likewise, those are the longest ones because the dots are farthest apart. So that's a nice looking motion map of that. All right, determine the displacement from time 3 to 5 using the velocity time graph. That's this one. So from time 3 to 5, so that's that area idea. The area of this is 6. Because it's 3 meters per second high and 2 seconds wide. How about from 7 to 9? That's right here. So that area is, it's negative 5 meters per second high. That's kind of a weird concept to have negative area. Your geometry teacher wouldn't like that, but for us it makes sense. 2 seconds wide, so that's negative 10. Okay. I'm not going to make you a special video just about average velocity and average speed, I decided. I think we're just going to have lots of chances to talk about it in the context of doing these problems. Just remember that average velocity is displacement over time, and it does not matter what happens in between. Average speed is equal to total distance. So it does matter when you have like turnarounds and stuff. Total distance over time. So sometimes these can be the same thing if there's never a turnaround, but looks like there is here. So let's see what happens. So delta x, we want to go from time 4 to time 8. So that's final. What's the position at time 8? It's 5. Minus initial, what's the position at time 4? It's 7. And then how much time goes by? 8 minus 4 is 4 seconds. So that's negative 2 over 4, negative 1/2 meters per second. That's the average velocity. Now what's the average speed? Well, average speed is total distance. So I just have to look at this and figure out the legs of this journey. So where am I starting at time 4? I'm at position 7. So it looks like it goes forward 3 and then eventually back 5. So that's 3 meters and then 5 meters. And total distance cannot have any negative parts. It's just all of the positive legs of the journey. So here, here. This was backwards, but I'm only interested in total distance here, not displacement. And that's 8 over 4, or 2 meters per second. All right?